In this video, I'm going to give an introduction to indefinite integrals and the concept of the antiderivative. So this is section 6.1 in Hawks. So first, here's the basic definition. Given a function little f, an antiderivative of little f is another function big F with the property that for all numbers x in the domain of f, big F prime of x is little f of x. In other words, the antiderivative of little f is a function whose derivative is little f. So we are going essentially the reverse of taking a derivative to get to an antiderivative. One thing that you should be aware of is that functions have lots of different antiderivatives, but all of those antiderivatives are the same up to plus or minus a constant. So let's take an easy example. Suppose I'm looking at little f of x equals 3x squared. Well, here are three different antiderivatives of little f. The first, here big F of x, is x cubed. And you can check that this is an antiderivative of little f because the derivative of x cubed is 3x squared. But if you look at this next function, big G of x equals x cubed plus 5, well, the derivative of big G of x is 3x squared plus 0, because the plus 5 contributes plus 0 to the derivative. Same thing happens with big H of x. If big H is x cubed minus 13, the derivative of big H is 3x squared. And again, this is happening because a constant added to or subtracted from a function changes where the graph is up and down in the coordinate plane, but it doesn't change its slope anywhere. It doesn't twist the graph or stretch it in any way. It just slides it straight up and down. So all of the tangent lines have the same slope with or without this added constant. Okay. We will often speak of a general antiderivative of f, and that is written as you find any antiderivative and then add an unspecified constant. It's usually plus c. Sometimes we'll use k or some other letter if c is already used for something else. C is an unspecified constant here called a constant of integration. So this formula that you're seeing here, big F of x equals x cubed plus c, encapsulates all of the different possible antiderivatives of this function little f of x equals 3x squared. Now, the notation for a general antiderivative of a function is something called the indefinite integral. The symbol here, sometimes called an integral sign, is actually a tall S. For example, here's a little bit from the Declaration of Independence, and here's a little bit from an old version of the Encyclopedia Britannica. These days, we don't write tall S's like this. It's too easy to confuse them with F's. But in 17th and 18th century handwriting and typesetting, that's one of the symbols that they used, and this was a symbol that was chosen for reasons that I will not have time to get into in this lecture. The dx here is similar to the dx that you would see in a derivative, dy over dx. So this is in some ways derived from Leibniz's notation for the derivative. Now, you may also be wondering if there's such a thing as an indefinite integral. Is there such a thing as a definite integral? There is. That will have to wait for another video. Okay. Now, all of the rules that I'm about to show you for antiderivatives are derived directly from derivative rules. And just to give you a little bit more of an explanation, if you wanted an antiderivative of 3x squared, well, the derivative of something that would have an x squared in it, you could imagine that you maybe used the power rule on something to get that x squared. You would need to go up a power, because remember, when you do the derivative power rule, the power goes down a degree. So that means that you would expect the antiderivative of something with an x squared in it to have an x cubed in it. And so with a little bit of guesswork, you can see that x cubed is exactly what we need. We can write down some slightly more systematic rules. So let me show you what these are. So first rule is, suppose you have multiplication by a constant and you need the antiderivative of that. Well, it's just like the derivative of multiplication by a constant. You keep multiplication by the constant and then just continue with the antiderivative of the rest of the stuff. If you have an antiderivative of an expression that has two things added together, then, well, you do the derivative of the antiderivative of the left part plus or minus the antiderivative of the right part. Be careful with the subtraction that you get enough parentheses in the right places, because you need to be sure that you subtract the entire antiderivative of the right from the antiderivative of the left. Now, the power rule for an antiderivative comes in two parts. The first is for a power other than -1, the antiderivative of x to the m is, well, it's x to the m plus 1, but we have to compensate here by putting in a factor of 1 over m. Let me briefly explain why. So suppose that I say that little f of x is equal to x to the m, and I want to construct a big F of x whose derivative is x to the m. Well, I could try big F of x equals, and again, thinking I've got to use the power rule, got to use the derivative power rule on something over here to get me back to x to the m, I need to go up to the next power up. But if I actually compute the derivative of that function big F, I'll get big F prime of x equals, and remember how this works, you get a factor from the power times a new power that's the old power minus 1. Now, that's pretty close, but we need to do something about this. So let's try again. What I'm going to do is leave the x to the m plus 1 in place, but now I'm going to put a 1 over m plus 1 right here. And again, the goal is to get something here whose derivative is just x to the m. So let's check this. One over m plus 1 is a constant that multiplies the rest of this stuff. So I keep 1 over m plus 1. Then I apply the power rule to x to the m plus 1. I get a factor of m plus 1 and a new power that's the old power minus 1. And this time, because I've put in this correction, it cancels out, and I am left with f prime of x equals x to the m. So, in short, this is the antiderivative that we want. And sure enough, there it is. There's the rule. I've written a plus c here in gray. When you look at lists of rules for antiderivatives, sometimes they'll put a constant of integration, a plus c, in for each rule, and sometimes they leave them out because you're supposed to just know that the general antiderivative has this unspecified constant at the end. You'll just have to look at the table of integrals and understand that some use one convention and some use the other. Now, I said that there was a special case. We have to do something different if m is equal to minus 1. What goes wrong if m equals minus 1 is that right here we would be dividing by 0, and dividing by 0 is not a good thing. It's undefined, causes problems. So this rule cannot work for a power minus 1. So here is the power rule in the case of power minus 1. The antiderivative of power minus 1, which by the way is the same as the antiderivative of 1 over x, is the natural logarithm of x. Now, for sort of technical reasons that I can get into, you need absolute values here. It turns out that if you only include x there with no absolute values, then you kind of miss an important half of this rule that sometimes comes into play when x is taking on negative values. I will demonstrate more about that later. And again, I've written the plus c here in gray because sometimes it's written in the table of rules and sometimes it isn't. Okay, well, for the exponential rule, I'm going to do only some very simple examples with the exponential rule. The antiderivative of e to a power that is a constant times x is 1 over the constant times e to the constant times x. Now let me show you how to check this. I'm going to let big F of x be 1 over a times e to the ax. F prime of x is, well, we keep multiplication by 1 over a. We then recognize that that's e to a power, and so we need the exponential rule. And the derivative of e to stuff is e to the stuff. But then since the stuff up here has another operation in it, we have multiplication of the constant a times x, we need another term, we need a chain rule term, and that's the derivative of ax. And the derivative of ax is a. And now you can see, I hope that, let me use this one, that the point of putting the 1 over a here is so that it cancels out with that a that comes out of the chain rule. So we end up with just f prime of x equal to e to the big A x, and we're happy. So that is checking the easy exponential rule. Now, I should mention a couple of things. One is that there is a version of the product rule for antiderivatives, but I'm not going to get into it now. I usually don't have time to do that in Math 105. There's also an antiderivative version of the chain rule. That's called a U substitution, and it's for dealing with things that are kind of like this, but maybe a little more complicated. And again, I'm not going to get into that in this lecture. I'm just giving you the basic rules. So with these rules, we can do the antiderivative of any polynomial. We can do the antiderivative of anything with a 1 over x in it. And we can do antiderivatives of certain exponential functions. Okay, so with that, I'm going to end this introduction, and in another video, I'll do some examples.